In this video, we will look at Kirchoff's laws. We'll look at Kirchoff's first law, Kirchoff's second law, and we'll apply these laws to two electrical circuits, right? So let's look at Kirchoff's first law, or Kirchoff's current law. So Kirchoff's first or current law, right? So Kirchoff's first law is also referred to as Kirchoff's current law, and vice versa. So according to Kirchoff's first law, the algebraic sum of the currents at a junction in a circuit equals 0. Right? So according to Kirchoff's first law, the algebraic sum of the currents at a junction in a circuit equals 0. So mathematically, we may write this as the algebraic sum of I is equal to 0. Now, what exactly does this mean? In simple words, this basically means that the total current flowing into the junction, so the total current flowing into the junction must equal the total current flowing out of the junction. Total current flowing out. Right? So according to Kirchoff's first law, the algebraic sum of the currents at a junction in a circuit equals 0. And in simple words, this means that the total current flowing into the junction must be equal to the total current flowing out of the junction. Right? So let's look at an illustration and see if you can try to visualize this. Now let's say we have a junction in the circuit where we have a few wires carrying currents in different directions. So these wires carry currents I1 and I2 into the junction, and these currents, or these wires rather, carry currents I3, I4, and I5 out of the junction. Now, according to Kirchoff's first law, the total current flowing into the junction must be equal to total current flowing out of the junction. And therefore, we can say that I1 plus I2 is equal to I3 plus I4 plus I5. Right? Now, essentially, so far, we have looked at circuits involving one battery and a combination of resistors. And in some cases, some of these resistors were connected in parallel, which means that basically the current being driven by the battery had multiple paths to flow. And in a circuit like that, essentially we have been applying Kirchoff's current law without actually have been introduced to Kirchoff's current law. So if we have a circuit like this, where we have, for instance, 3 resistors connected in parallel, right? And we have a battery connected across them like that. And this battery is driving a current I, right? So at this junction, the total current flowing into the junction is I. And let there be individual currents I1, I2, I3 flowing out of the junction, right? Now, according to Kirchoff's first law, the total current flowing into the junction I must be equal to the total current flowing out of the junction, and so we say that I is equal to I1 plus I2 plus I3. Alright? So this is basically Kirchoff's first law. Now Kirchoff's first law is based on the principle of conservation of charge. Now you would have met principle of conservation of energy, and you ought to have also met the principle of conservation of momentum, and by now you should know perfectly well what it means when you say that momentum is conserved as well as when you say that energy is conserved. Now let's think about electric charge and current. Now we know that basically electric current is the rate of flow of charge. So if there's a certain amount of charge flowing per unit time, then we have a certain electric current. So if we have a current of, say, 5 amperes flowing past a given point in a conductor, This basically means that we have 5 coulombs of charge flowing per second. So if we have a steady current of 5 amperes flowing past a given point in a conductor, it means that basically every second we have 5 coulombs of charge flowing past a given point in the conductor. Now let's think about a junction. Whenever there's a steady current flowing, then it means that basically charge cannot accumulate at the junction, neither can it deplete, which therefore means that the total amount of charge that flows into the junction must be equal to the total amount of charge flowing out of the junction. And we say that basically that charge is conserved. So therefore the total charge flowing into the junction must be equal to the total charge flowing out of the junction. And if we think of this per unit time, then the total charge flowing per unit time into the junction, that is the total current flowing into the junction, must be equal to the total charge flowing per unit time out of the junction, which of course is equal to the total current flowing out of the junction. So again, Kirchoff's first law is based on the principle of conservation of charge, and this basically means that the total charge flowing into a junction per unit time must be equal to the total charge flowing out of the junction per unit time. And since current is the rate of flow of charge, then it basically means that the total current flowing into the junction must be equal to the total current flowing out of the junction. Alright, so that is Kirchoff's first law. We'll now examine Kirchoff's second law. So Kirchoff's second law, which of course is referred to as the voltage law. So Kirchoff's second law, which is referred to as Kirchoff's voltage law, which of course you may see sometimes as KVL, right? Kirchoff's current law may be represented as KCL and the voltage law KVL. Now, what exactly does Kirchoff's second law state? Kirchoff's second law states that in any closed loop of a circuit, the algebraic sum of all the EMFs in the circuit must equal the algebraic sum of the PDs across all the resistances in the loop, right? So according to Kirchoff's second law, or Kirchoff's voltage law, in any closed loop of a circuit, the algebraic sum of all the EMFs in the circuit must equal the algebraic sum of the PDs across all the resistances in the loop. So mathematically, we may write this as the algebraic sum of the EMFs E is equal to the algebraic sum of the potential differences across all the resistances in the loop, right? So basically, what this is saying is that if, let's say, all right, so yes, since we already have a few circuits here, let's examine one of these circuits and see what Kirchoff's second law is basically saying. Now, Kirchoff's second law is basically saying that in any closed loop of a circuit, the algebraic sum of the EMFs in the circuit or in the loop must be equal to the algebraic sum of the potential differences across all the resistances in the loop. So in applying this to circuit, we must identify a loop of the circuit that we want to traverse. We must basically identify all the batteries or the sources in the circuit and find the algebraic sum of their EMFs. We must also identify all the resistances in the circuit and find the algebraic sum of the potential differences across all these resistances. And then to apply Kirchoff's second law, this algebraic sum of the EMFs must be equal to the algebraic sum of the potential differences across all the resistances in the loop. So now that we've stated Kirchoff's first and second law, we'll then go ahead to applying it to these circuits.